terms of the context of where it belongs in the class. So you might think of what we've done so far in the class as like we've introduced new and more interesting families of functions. We started with like linear functions, we talked about parallel functions, quadratics, general polynomials, rational functions, and today I'm going to introduce, instead of just a new type of function, an operation you can do to functions. We'll talk about involving functions. And I don't know, just like, I like to see this with lots of topics. So how many people in this class, if I say I want to invert a function, already have a pretty good idea what it means? Cool, yeah, what's it mean? Sorry, I didn't say that was going to be a follow-up. Okay, cool. Let's talk about inverse functions. So the idea of a function is it's like an action you can do to some numbers. A function is some set of instructions you can apply to some inputs, and it spits out an output. It doesn't even have to be numbers. A function can have whatever as inputs and whatever as outputs you want. Inverse functions are what you get when you try to undo that action. They're what you get when you try to start with the output and figure out what the input is. Yeah.
So when you make like x, y, and then you have to like resolve for x.
Yeah. That is the algebraic way to think about finding inverse functions. Because you want to swap inputs and outputs. You want to think of the output as now the input and figure out what input would produce it. So that's exactly it. So let's start leading into it. So let's start with the following. Here are some, I think, reasonably straightforward exercises. Take a moment for me, if you would. Solve that equation. X cubed plus 2 equals 1. Tell me what you get. Or should I talk through it? People getting hung up on any of the algebra? Okay. Cool. Once you have the solution, check it against those around you. Tell me what you got. What'd you get?
X equals the cube root of -1.
I hear an x equals cube root of -1. Do I hear a second? Do I hear it called to simplify? What is the cube root of -1? -1. Right, the cube root is what number can you cube to get -1? Ah, -1 will do. All right. Should I actually write anything? Cool. I'm going to have you do it again. That next equation. Solve that again. What do we get?
X equals cube root of -9.
Cube root of -9? Do I hear a second? Cool. Do I hear a call that I should go through any of the algebra? All right. So, I'm going to be a little bit annoying and say, oh, no, you don't need both negative signs. You can pull the negative sign out of a cube root. And you kind of should. You should simplify that. So that was somewhat inefficient, yes? You just did the same bit of algebra twice. And in each case, the type of question that was being asked was really similar. You had some function, the same function. I told you what output I wanted. and u gave me the input that goes to it. So whenever you have a bunch of really similar questions that you want to ask, you can get yourself a formula that just solves that equation by building the formula in the abstract and then using it. So just how like the quadratic formula solves any quadratic function, you could build like a formula that solves this equation. And let's see that in action. So let's abstract out a little bit. Let's leave that y as like a variable. And let's ask this, does that look like an equation that you could solve generically for x? Yeah, in fact, like you've already done it twice. Tell me what steps to do. You want to solve that for x? What seems like a good first step? What was the first step you did in the two up here? Subtract 2. That seems good. So x cubed is the same as y minus 2. All right. What next? Take a cubed root. Oh, and remember, cube roots are like kind of nicer than square roots in some ways. Cube root actually undoes the cubing function. You don't get this goofy plus or minus showing up. So, what is this formula? That gives a solution to x cubed plus 2 equals y as a function of y. And if you don't like that silly abbreviation of function, don't use it. I'm lazy, I want to write a few letters. Let's use that now. X cubed plus 2 equals 1. I guess we did just solve it, but let's see if our formula just agrees. So it looks like I want to set y equals 1 into this formula. So let's use it. I'll want to take the x equals the cube root of y is 1 minus 2. Yeah, that's the cube root. Negative 1, that's negative 1. That feels pretty good. So here's a reason to study these things called inverse functions, which I haven't even defined yet. If you have a bunch of really similar questions that you want to answer, it's useful to abstract out what's different about them, hold on to what's the same about them, solve the abstract equation, and then just use it. And like there are 3 examples here, but let's do the one that's actually new. So can you just read off the solution to that equation using the formula? Yeah, what do you get? I hear a cube root of 18? Yeah. You just want to plug in, it looks like y equals 20. So you get the cube root of 20 minus 2. Yeah, that's the cube root of 18. No perfect cube factors to pull out of that. Oh, let's make it so you can actually see what I'm writing. I'm sorry. That's the idea of an inverse function. If you have some function of the form f of x equals y, that takes inputs and spits out outputs. If you solve that for x to get x as a function of y, you have just undone that function. You found the inverse. That new function is often denoted f inverse of y. But notice, like, that's y being the independent variable and x is the dependent variable. So, like, that's the opposite of what you usually want the variables to mean. So you usually swap the role of x and y just for that reason. So in general, whenever you swap the role of x and y and then solve to get this new function f inverse function, that's finding the inverse function. So let's do one. We'll see if you want to do it or if I should do it. F of x equals 3x minus 2. Let's find the inverse function. So what does that mean? That means I need to swap the role of x and y, where I guess here the function I would want to call y. X equals 3y minus 2. Solve for y. And now that the actual just algebraic equation is written, that looks like something you can solve easy enough? Cool. Let me know what you get. Or should I do? Okay, cool. What'd you get?
X plus 2 divided by 3.
X plus 2 divided by 3. Do I hear a second? Cool. There should probably be some parentheses in there, yeah? Dot, 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 because I'm not doing the walk. So, in this case, the inverse function, the function that undoes that function, is x plus 2 all over 3. How do people feel about that? Idea familiar enough now that we actually see it? Nice. So, let's explore some things about inverse functions, and I think the next thing on the docket is what graphically can you say about them? But first, there's a subtlety about inverse functions. Sometimes you can't find them because they don't exist. So here's an example. Let's try to find the inverse function to f of x equals x squared. So that means we want to swap to all of x and y. So that's not the one you want to solve. You want to swap to all of x and y. So you want to solve x equals y squared for y. Sound look like something you could solve? Yeah, go through the walk. Do it. I guess there's only like one step, right? What do you get? Yeah, I'm going to write it in the other order because... Any disagreement? Oh, there should be a little bit. Oh, there should be a plus or minus. All right, whenever you undo a square with a square root, you lose information. And that's like a big deal. That says for any fixed x value, there are two different y values. Are functions allowed to do that? No, only one output per input. There's an input which for this function goes to two different outputs. If you try to plug in x equals 1, you get 1 and negative 1. That's not a function. It's still something. It's just not a thing that I would call a function. Maybe I'd make up some other word like relation to describe it. So, let's think about why that happened. So here we saw that one input x went to two different outputs y. And I think that corresponds to there being two different inputs for this function that both go to the same output. Up there, if you plug in 1 or negative 1, you get the same output value. So that means when you plug in 1 here, you'll get two different input values. Ah, well, that's kind of annoying. But let's just study when that happens. Let's make up a word for it. So whenever there are multiple input values, x values, which result in the same output value for f of x, then the inverse to f of x won't be a function. Fair enough? That's basically what this illustrates. So we'll make up some words for such things. A function is called one-to-one. Or sometimes, you know what, I'll drop the fancy Latin word because that might show up in some context that you see. Or injective. If every two distinct x values result in distinct values for f of x. So a function is one-to-one if no matter what two distinct x values you plug in, you'll always get different output values. So let's try to read off what this means. Oh, let's go back up here. So let's think about x squared. Can you give me two different inputs which have the same output value for x squared? There's a ton of freedom. 1 and negative 1 will do.
So here are two inputs, 1 and negative 1. Those are two different inputs, result in the same output. That sucker is not 1-to-1. And I'll use that shorthand for 1-to-1 sometimes. All right,
So this has something to do with graphs. And in order to see what it has to do with graphs, let's try to detect whether these functions are 1-to-1. So let's look at that force function. So by looking at that graph, can you find two different inputs which both go to the same output? Which two inputs are you thinking of? Be approximate if you want.
X equals -2, x equals 0, and 2.
Yeah, cool.
it looks like x equals 0, -2 and 2 all go to y equals 0. So if you want the output of 0, that output corresponds to 3 different inputs. This sucker is not 1-to-1.
Is there another output you see that has multiple inputs that go to it? What output are you thinking of? There are tons. How about y equals 1? How many inputs do you see that results in an output value of 1? 3 of them, I think.
So let's see, that's like, let's call that about -1.6, -0.5, and I don't know, about 3.2. Those all go to y equals 1.
So it's very not 1-to-1. In fact, maybe I'd want to call this function like 3-to-1. 3 inputs to 1 output. That's not a formal notation I'll use. How about this next one? For that function, do you see 2 different input values that all go to the same output? Ooh.
No distinct inputs go to the same output. So the second function, is it 1-to-1? Yeah.
And here's maybe a visual way to check that. Let's look at all the possible output values and see if there's an output value that corresponds to 2 different inputs.
And how do you do that? Well, you draw some horizontal lines. Right, horizontal lines will correspond to output values. How many times do each of those lines cross the graph?
Just the once. So each of those y values only comes from one x value. So you can look at a graph and tell if a thing's 1-to-1
using the so-called horizontal line test.
A function f is 1-to-1 if and only if, so exactly when, the graph of the function intersects every horizontal line and at most one point. So whenever you see a graph, if you want to see if it is invertible, if you can find an inverse function, perform the horizontal line test. If it passes the horizontal line test, then it has an inverse and you can start trying to find it. That seem okay? Nice. And in fact, this philosophy can get you a little bit more. It can even tell you what the graph of the inverse function will look like. And in order to see what the graph of an inverse function should look like, let's actually just find an inverse function. So here's a function that I'm not giving you a formula for. I guess it's a piecewise linear function. If you are sufficiently algebraically minded, you could find a formula for it, but I think I'm not going to. Let's try to find an inverse function just by looking at a few inputs.
So we're going to walk. Oh, maybe here this first.
That function, does it look 1-to-1? Okay, cool. So it has an inverse function.
So it's not silly to talk about finding the inverse. Let's try to find the inverse function by asking a sequence of questions. So, look at the graph of that function. Can you find me an input value that results in an output value of negative 3? No, ask what's actually written. 3. Can you find an input value that results in an output value of positive 3? What input value were you thinking of? Negative 2 will do. So I see this point up here at negative 2 comma 3. That tells me that an input value of negative 2 goes to an output value of 3. So that's exactly the job of the inverse function. The inverse function applied to 3 should give you the input value that goes to 3. So, what's f inverse of 3? 2. The inverse function applied to an input asks what input would go to that output. Negative 2 goes to 3. So the inverse function of 3 should be 2. And that's maybe even worth writing in words on the bottom. If you want f inverse of any input value, find the input with f of x equal to that value. Inverses swap inputs and outputs. Alright, so f inverse of 3 equals 2. That means if I want to graph the inverse function, I would have the point... Oh, god damn it, I'm losing negative signs all over the place. Is that why people are looking upset at me? You can just correct me when I make a mistake. X equals negative 2 goes to y equals 3. So f inverse of 3 will be negative 2. Negative 2 is the input that goes to positive 3. So that means that 3 comma negative 2 will be on the graph of the inverse function. Because if I plug this x value in for that formula, I'll get an output value of negative 2. And now I'm going to flip to the next page, and I'm going to draw the point 3, negative 2 on the graph. There was just a really unfortunate page break here that I couldn't avoid. No, which means that 3, negative 2. 1, 2, 3, negative 2. And that came from the point negative 2, 3. And I'll try to color code the connection between them. All right, let's ask a sequence of similar questions. Could you use the same philosophy to tell me what is f inverse of 1? So, by looking at the graph that you see there, what input value goes to an output of 1? Negative 1. An input of negative 1 goes to an output of 1. So, f inverse of 1 is negative 1. So the original function sends negative 1 to 1. So the inverse function has to do the opposite. It has to send 1 to negative 1. Nice. All right, I'm going to flip over and graph that on the next page. So because of this point, negative 1, 1, I wind up with the point 1, negative 1. All right. Do you think you can answer the next two questions? To do so, use the philosophy given in this sentence. I'm going to establish the color coding.
All right, tell me, what is f inverse of 0?
0.5 or 1/2-ish.
Why that? How'd you get that?
Isn't that this point here?
Ooh, that's f of 0. I want the opposite. So to get f inverse of 0, color code. Did I ask 0? I asked for 0 right now, right? Yeah. So to answer that question, I want to know what input gives f of x equals 0. So whenever you want to have an input value for the inverse function, you're really thinking of that as the output for the original function. Inverse functions swap input and output. So, now look at the graph. On the graph, what x value gives you a y value of 0? I think a 1. There's this point here, 1, 0. So x equals 1 gives you an output value of 0. So f inverse of 0 is right. Inverse functions swap inputs with outputs. All right, last one left on the list is f inverse of -3. So to compute that, what input gives you an output of -3? Say louder. 2. Do I hear a second? Nice. Yeah. F inverse of -3 equals 2. What point on the graph told you that? This one down here. The one at 2, -3. All right. So now I'm going to encode that information on the graph on the next page. So, and I'll try to even remember the color coding. This point at 1, 0 gave you the point here at 0, 1. This point here at 2, -3 gave you the point at -3, 2. And, well, you know what? Here's something that hopefully just seems intuitive. That straight line, when you take the inverse, is going to give you the straight line between the same two color-coded points. This straight line is going to give you that straight line. So there now is the graph of the inverse function. And let's just ask a question about this real quick. How do those two graphs compare? Is there some sort of relationship between them? Let's think about the color coding. The black point in the top left, that like became the black point in the bottom right. How are those 2 points connected? How are they related to each other? So let's see, it went from 2, -3 to 3, -2. So it looks like those coordinates just swapped. From -1, 1 to 1, -1. The coordinates swapped. Oh, cool. Here's a connection between the graph of a function and the graph of the inverse function. If f is a one-to-one function, then the graph of the inverse function is given by, I'm going to write this 2 different ways, swapping the x and the y coordinates. If you want to know what the graph of an inverse function looks like, just swap the role of x and y all throughout. And there's like a symmetry way to do that. This is equivalent to reflecting over the line y equals x.
And maybe just to convince you of that, let's draw on this graph the line y equals x to the best of my ability. And let's just see what happens when I reflect some points over it. So if I take this orange point and I reflect it over the line y equals x, yeah, it looks like I get the same point with the opposite coordinate, with coordinates swapped. If I take the blue point, do the same, yeah, it looks like I get the blue point.
Yeah. So geometrically, you can swap coordinates by reflecting over the line y equals x. This does mean that, like, if you just want the graph of the inverse function, it's free. The graph of the inverse function is the same as the graph of the original function, just with x and y values swapped. Yeah.
Can you show me that x equals y line with the elliptic graph?
Oh, yeah.
So happily, if you swap the coordinates of x equals y, you get y equals x, which is the same. And then let's maybe check the same. If you take this blue point and reflect it over that line, you get the original blue point. If you take the orange point, reflect it over that line, you get the original orange point.
And the only reason I'm not doing it with the far away points is, like, it's just visually harder to be convinced that you're doing it correctly when they're too far away. No, it's not.
Don't be a coward, Chris. You have this point at negative 3, 2. That's 1, 2, 2.5 blocks I had to go diagonally across. 1/2, 1, 2. So that point 3, negative 2 should come from that point, and indeed it did. Cool. That feel pretty good?
So let's use this now just to do something that a computer can do automatically and for free.
So let's suppose that I asked you to find the inverse to this function.
And we'll do it algebraically in a moment. But before we do that, let's get the graph without doing any work, using a computer. So, let's see. I'm going to pull up pre-made little Desmos Interactive. There's the graph of this rational function. Does it look right? Does it have a vertical asymptote where you expect it to? X equals 2?
No, shoot, let's just check these to be sure. X equals 2. Cool, yeah, vertical asymptote. Where should its x-intercept be? Looks good. How about its y-intercept? Looks good. How about its horizontal asymptote? Cool, yeah, then that graph all looks correct. If you want to graph the inverse function, you could apparently just swap the role of x and y. Desmos is perfectly happy to do that. X equals f of y. So you want the inverse to the function? There's what it looks like. And maybe we'll even take a look at that. Let's make it a little bit bigger. No, we'll do this. I'm getting ahead of myself. So if you want the graph of the inverse function, there it is. You can get it automatically, just swap the role of x and y. You can also do it algebraically without too much work, and I think it's worth doing the algebra in this case because it's also a good demo in how do you work with rational functions. So let's try to find the inverse to this function. To do that, what equation do you need to solve?
Y minus 1 divided by y minus 2 is equal to x.
Nice. So you take all the x's in the formula, you replace them with y's, you replace f of x with just x.
If you can solve that equation for y, you now have a formula for the inverse function. And maybe we'll see how people feel about this bit of algebra. It's not necessarily hard, but if you don't like see see the trick to get you started, then it's basically impossible. Does anyone not see how to get started and wants me to get them started? Cool, let's do. So, let's take a look at what you see there. I want to get y on its own. There are two y's on the left-hand side, that's kind of annoying. But otherwise, what's like the most complicated operation on the left-hand side? Division. So let's try to undo that division by doing something to both sides. What would you want to do to both sides of that equation to get rid of that division? Yeah.
Multiply by y minus
Multiplied by y minus 2. And that is often described under the buzzword cross multiplication. So let's cross multiply. Y minus 1 over y minus 2 multiplied by y minus 2 equals x times y minus 2. And so maybe in your walk you would like suppress that step, but it's nice to see like what you're doing to both sides. So the whole point of making that step is now the side that used to be more complicated is now not as complicated as it used to be because the y minus 2's will cancel. Multiplication and division undo each other. So you will wind up with y minus 1 equals, and I don't know, the other side of the equation, like maybe we just distribute. Let's distribute and see what happens. xy minus 2x. And remember, our goal is to solve this for y. So eventually we want to get y on its own. So maybe it's a good idea to get all the y's onto the same side and get all the non-y's onto the other side. That seems sensible enough? All right, what operation should I do if I want to get all the y's onto one side and all the non-y's onto the other side?
Addition, subtraction.
Do some addition and subtraction. Be specific.
Add 1, subtract xy.
Add 1 to both sides, subtract xy from both sides. How many people did like the exact opposite, so they got the y's on the other side when this one's going to? Oh, if you did, it would have been just fine. You get maybe a different looking answer, but it would also be correct. So doing that, so you wind up on the one side with y minus xy. That's nice, all the y's are on the same side, equals 1 minus 2x. Or maybe you put minus 2x plus 1. I feel like having the subtraction second is better. All right? And remember, I want to get y on its own. So what can you do on the side with the y's that makes it easier to get y on its own? I guess try to isolate the y's.
Factors.
Everything on the side with the y's has a y, so we can factor out a y. Not doing anything on the right-hand side. When you factor out a y, what are you left with? 1 minus x. Right, when you pull a y out of a y, you're left with 1. When you pull a y out of an xy, you're left with x. All right? So on the side with the y, I see y multiplied by some stuff. I just need to get rid of the multiplied by some stuff. How do you do that? Divide by that stuff. Cool. Does that agree with the answer that everyone got who did things just independently? How many people instead got walking independently 2x minus 1 divided by x minus 1? Is that the same? I think it is. You can multiply the numerator and denominator by minus 1. So the point here is that maybe you'll get different looking rational functions when you invert things, but those are the same expression. In fact, I would probably want to think of this as being the simpler one. Right. Usually you have your polynomials written with the x's before the constants. Anyway, cool. So you can algebraically find inverses to rational functions.
The trick is cross divide, get y onto one side, factor, divide. Neato. That feel pretty okay? Is there anything we could do like graphically to check if this is correct? Do we already know what the graph of the inverse function should be? Yeah, we like just did that. So let's do that. Click. So that blue thing is the graph of the inverse function. And we have a formula. Y equals 1 minus 2x. Nope. Minus 2x. Divide by 1 minus x. God damn it. Might look like it's basically the same. Nice. And maybe just in case, like, there we go. So that other formula is in fact the same again. Groovy. That feel okay? All right. So let's notice some things about these involving domains and ranges. So the payoff that I'm going to try to get in the next couple of lines is what are the domain and range of an inverse function, and how do they interact with the domain and range of the original? And maybe that's actually what starting up here. By looking at this graph, what's the domain of the function in black? So that's f inverse of x. What's the domain of that function?
Negative 3 to 3.
Negative 3 to 3. The domain is the x values on the graph. Oh, what's negative 3 to 3 in terms of this original function? The range. Domain of the inverse function is like the same as the range. And notice that makes a lot of sense. The x and y values just swapped. Domains and range are just x and y value things. So since the domain of a function can be read off of a graph by just like all x values on the graph, and the range of a function can be read off as all y values on the graph. If you have a one-to-one function, the domain of the inverse function is the same as the range of the original function. The range of an inverse function is the same as the domain of f of x. That feel pretty okay? Nice. And let's see. Let's see, with 7 minutes, so all of that example, this next example goes through is checking that the function and inverse function we just found satisfy this condition. But I think it might actually be more worthwhile to close with the most technical thing from today, which is also posted as the open-ended for today. I'm pretty sure. Should be, anyway. So all of that is like the idea of what the inverse function is. The inverse function is the function you get when you swap the role of input and output. It's useful because if you want to solve a bunch of similar equations, finding the inverse function just lets you do it. Lets you undo a function. Here's the actual definition of inverse function. If you have a function f of x, the inverse function f inverse of x is the unique function satisfying the following composition results. If you do f of x and then undo f of x, you should always get x back. If you undo f of x and then you do f of x, you should always get x back. Both of those rules seem sensible enough?
right? If you do something and then undo it, you should get back to where you started. Let's see if this actually holds up by checking it for the function whose inverse we just found.
So what did we just get f inverse of x to be? I have a very bad memory. Remind me. I could flip the page, but I don't want to.
The last problem.
Yeah.
Negative 2x plus 1 over 1 minus x.
Nice.
Let's check if that's actually correct.
And the way to do that is we need to check that two equations hold. We need to check that both of those compositions always just give you x back.
And, well, I think we have enough time to probably do one of them. Which one should we do? First one or second? It doesn't matter. Just do first. There's no reason to guess. So let's check this first one.
So in order to do that, I like some color coding when I do composition of functions. So what does composition of functions mean?
That means I should take the formula I have for the inverse function and plug f of x in for the x's in it.
So that will be negative 2 f of x plus 1 all over 1 minus f of x.
All right. We have a formula for f of x, though, right? Let's use that.
That'll be negative 2 x minus 1 over x minus 2 plus 1 all over 1 minus x minus 1 over x minus 2.
And apparently that's supposed to be the same thing as x no matter what x we plug in. So I guess that means like we know that this should simplify down to just x, but actually doing so might take some effort. And let's go through that effort. So there's the thing you'd want to simplify. How would you want to simplify it? There are a few plans of attack. Well, how about this? Let's just look in the, focus just on the numerator. If I asked you to simplify that and write that thing in the numerator as a single function, could you? What would you have to do? Yeah, I guess you could. You could distribute the 2 onto the stuff on top. You need to get the 1 to have a common denominator also. So let's do both of those. Let's distribute that 2 into the numerator of this fraction. Let's write that 1 as something with an x minus 2 in the denominator. So let's see, that's minus 2x, 2 times negative 1 is plus 2, divide by x minus 2, plus. So I want to write that 1 as something with an x minus 2 in the denominator so that I can add fractions. What should the numerator of that fraction be? Yeah, right? X minus 2 over x minus 2 is 1. And let's do the same thing in the bottom. How would you want to rewrite this one? Nice. And you know what? As long as we're in the spirit of distributing, let's distribute this negative over that fraction. All right, cool. The whole point of getting a common denominator is so that you can add fractions.
So now that I've gotten the common denominator, I should add some fractions, right? Let's add those fractions. So let's focus just on the top. Big division bar, give me some space, divide by x minus 2. Alright, so when you add those fractions, what's the total you get in the numerator of the numerator? What goes in that topmost parentheses? Well, I guess maybe in the interest of time I should speed up. So add to fractions by just adding the numerators now. Negative 2x plus x gives me negative x. 2 minus 2 gives me 0. So just negative x on top. In the bottom I see x minus x is no x's. Negative 2 plus 1 is negative 2. Alright, well that got simpler. Let's see. Next thing I notice is I divide both the numerator and denominator by the same thing. Those cancel. Negative 2 minus 1 is negative 1, not negative 2. Alright, so this looks like it reduces to just negative x over negative 1. What does that simplify to? X over 1, which is just x. Oh, cool. That's exactly what I knew it should. That now verifies one of the two equations that I need to check in order to know that this is actually the inverse. So here is what the homework posted for today, for the open-ended, is. Verify that a given inverse is actually the inverse. And right after this section in the notes, there's like a couple more exercises posted. I'm bad at ending class. You should be happy right now. Ooh, and let's see. I have my office hour today at the 10. 10 to 11. Let's make it 10:50. I have a high priority meeting right at 11. Like a meeting, I'll get in trouble if I don't.
We don't want to get fired.
I don't think it's that bad.
No, not that bad.
I think it happens to you fine.
Do you get sick days?
In a sense. I mean, right, like, yes. No, in fact, formally I have sick days. I have to track them. I have to enter in every month into an online system if I don't take any sick days.
Do you get money back for it? Like you cash it in?
In a sense, like that money then goes towards like
Your class?
retirement healthcare stuff.
Oh, okay.
Yeah.
So the midterm is on everything before this?
Yep. Here's the better answer to that question. I am going to get to the course webpage, which you know how to find? Okay. So let's see, background quiz. A review for the course midterm, a review.
Okay.
If you like go through this, it's like 9 pages of stuff, so it's like way longer than the actual midterm. Oh, that's a weird place to have the line. Take a look at it, see how it seems. If you can answer all of these, then you're pretty solidly prepared for the midterms.
Okay. Should I, do you think I should do all 9 pages? Or?
Yeah, but like not all at once.
Okay. Yeah.
Well, here's what you should do. Right, like, look at a problem. If you say to yourself, I know how to solve that problem, and it's like something that takes an algebra walk, if you think it would be worth your time doing the algebra, then do it.
Okay.
This one is not one that has a lot of hard work in it, so that one you would just do if you know how to do it.
Okay.
Otherwise, you would need to review how to determine whether a polynomial has... Oh, I didn't give you buzzwords. The discriminant is what you would need to review.
Okay.
Yeah.